given by Abhinav Nath from the University of Washington in Seattle. And the title will be Understanding How Chaperones, Polyanions, and Novel Small Molecules Modulate Tau's Aggregation Pathway.
While we're waiting for this to come up, I just want to take a minute to thank Samrat and Betsy and everyone who made this meeting possible. It's really fantastic to be back home in India and part of a meeting like this. So, so I'm an assistant professor of medicinal chemistry at the University of Washington in Seattle. And before I dive into the science, I want to take a minute to thank the people in my lab who've actually done the work. I'm going to talk about work done by graduate students Hannah and David and postdoc Ari. And thanks obviously to collaborators. I've sort of highlighted some IDP-related people. Some of them worked on the projects I'm going to talk about, and others worked on different projects, and obviously funding sources. So obviously for this audience, I don't need to, first I need to flip slides. There we go. All right. So obviously, you know, I don't want to belabor kind of the basics of amyloid formation, but it's worth thinking about the fact that, you know, we have, across all of these diverse sequences, we have similarities in structure in terms of the fibrillar beta sheet structure. We have these similarities in kinetic mechanism, right, where we have a sigmoidal aggregation time course that can be shortened or ultimately bypassed by seeding. And certainly for the pathological non-functional amyloids, there's sort of a similarity in dysfunction where that toxicity is coming more from the intermediates in the aggregation pathway than the final fibrils. And we saw yesterday in the talks from Dr. Gankar and Dr. Dobson and many others, the value in thinking about sort of these aggregation mechanisms using models like this. So we've got here the sort of nucleation, elongation, fragmentation type models of amyloid formation. And one of the questions that I'm focused on is to try and understand when we have these different binding partners that can come in and interact with aggregation-prone proteins, what are they actually doing on a mechanistic level? If we have polyanions coming in, what process or what part of the process are they affecting? When we have molecular chaperones, how are they inhibiting aggregation? And then ultimately, can we take our understanding of these aggregation mechanisms, of the structures of the players involved, and use those to develop potentially new small molecule ligands, new modulators of these aggregation processes. So for the short talk, I just wanted to give you a flavor of sort of three different areas of effort in the lab. And the first is understanding how different classes of chaperone interact with tau, or the K18 fragment of tau. And so this is work done by graduate student Hannah Bothman in collaboration with Rachel Clevitt. And we started off trying to understand the behavior of two sort of prototypical chaperones on tau aggregation. We have a small heat shock protein, HSPB1, and an HSP family chaperone called HSC70. And so HSPB1, like other small heat shock proteins, the name is maybe a little bit of a misnomer, because you have these proteins exist sort of as a stable dimer, but they can self-associate into much larger oligomers. And the conventional thinking about these small heat shock proteins is that the substrate binding happens at the central alpha crystalline domain, and then you have disordered C-terminal regions and a disordered N-terminal region, and these are responsible for the oligomerization and the complex formation of things like that. And then with HSC70, again, the conventional thinking is that you've got a nucleotide binding domain and a substrate binding domain, and sort of the refolding of a target of a client is dependent on ATP hydrolysis. And in the course of this project, we actually found that both of these proteins are behaving a little unconventionally. In the case of the HSC70, it's able to inhibit tau aggregation in the absence of ATP. And this is something that's been seen with HSP70 family chaperones for alpha-synuclein, and actually lots of plant HSP70s do this as well with different clients. And then with HSPB1, I'm not going to talk about it in any real depth, but we found that you don't need substrate binding in the alpha crystalline domain. So you can use a mutant to block substrate binding there, and the protein still is a very effective chaperone. If you lose the N-terminal region, you lose the chaperone activity. And using paramagnetic relaxation enhancement, we know that tau actually interacts more closely with the N-terminal region than it does with anything else in the protein. So that's something we're sort of working on is if we isolate this N-terminal domain, this disordered domain in different contexts, in different architectures, can we preserve some of that chaperone activity? But taking a step back, if we just look at the kinetics of tau fiber formation in the presence of these different chaperones, so we've got the nice sigmoidal time course. As we titrate in HSPB1, we see an increasing lag phase. So we're just shifting the T50 to longer and longer times. I should say we're using a construct of HSPB1 that is limited to form a dimer. We've done this using 1D NMR with wild type and other constructs as well. So that seems like a fairly good inhibitor. You know, if you have a 1-to-1 complex, you've pushed the T50 back by about twofold. HSE70 is much more potent. So HSE70 has very little effect on the T50, but it's dropping the plateau, as you can see. And you know, even sort of 1 to 100 or 1 to 50 of HSE70 is enough to cut amyloid formation about in half. So we did electron microscopy to make sure that this is not some photophysical artifact of the thioflavin T dye that we're using. And so you have these nice fibrils of tau. If you take the endpoint of the HSPB1 reaction, you still have fibrils. They look a little uglier. We don't know what the origin of that is. But if you look at the endpoint of the HSC70 reaction, you see these much smaller oligomers. You don't see very many fibrils at all. So we're interested in understanding, right, what these different chaperones are doing to the aggregation pathway. And so we did sort of a classic experiment, which is to add the chaperone at different times in that aggregation time course. And so what the triangles are showing are the effects on tau fibril formation. If we add HSPB1 at the start of the reaction, it acts as an inhibitor. 30 minutes in, it's still able to inhibit. An hour in, it's almost ineffective. And once you're in that sort of, you know, once you've started to convert, HSPB1 is basically ineffective. So it only works at the very start of the aggregation formation, and even fairly early lag stage stuff is you know, letting tau evade its activity. Whereas HSC70, wherever you add it, it's able to just block fibril formation, to arrest it at that point. And so in trying to understand what was happening, we used NMR to sort of look at the binding of tau and tau to these chaperones. So we label tau, and we're looking for both chaperones actually cause peak broadening. So there's a loss of intensity upon complex formation, and we can use that to figure out where in the sequence are these chaperones binding. Are they binding to different parts of the target? And it turns out they're binding to more or less the same parts of tau, and these regions include sort of the, you know, the 2 hexapeptides that we think of classically as driving the aggregation of tau. There's a difference in affinity for sure. So using FCS, we can monitor the change in hydrodynamic radius as we add chaperones. And HSC70 has an apparent KD of about 100 micromolar, so it's not a very tight binder. And so this doesn't really jive with the fact that it's a substoichiometric inhibitor of tau fibril formation. So we used NMR to dig a little deeper and to try and see if there was some difference in selectivity or specificity for, say, particular states of tau. So heparin induces tau aggregation. It also induces chemical shift perturbations in the spectrum of tau. And so what we see with HSPB1 is that we have, you know, if we have heparin by itself, that's that gray thing that isn't really coming through, but trust me, there's a peak there. You have that peak shift with heparin alone. You have that same peak shift and the same peak intensity with the heparin plus the HSPB1. So there's no sort of cooperativity, there's no synergy in the binding. Whereas with HSC70, we see enhanced peak broadening in the presence of heparin. The ternary complex of HSC70 plus tau plus heparin is a higher affinity complex than the binary one. And so our sort of qualitative picture of what's happening is something like this. So HSPB1 doesn't have a lot of selectivity in terms of what form of tau it's binding, whether it's binding the native disordered state or the aggregation-prone, still disordered heparin-bound state. Whereas HSC70 is selective for that aggregation-prone state. We believe it's able to bind oligomers, and we believe that it's able to cap fibrils, and that's how it's arresting aggregation. So these are sort of qualitative conclusions. In order to get more quantitative information, we are looking at different sort of numerical modeling approaches. One of which is sort of an alternative to the type of very elegant analytical models that Thomas Knowles has come up with, where we're basically using Bayesian computation to take a system of ordinary differential equations that describes, say, this nucleation-dependent polymerization or nucleated conformational conversion or whatever your favorite model is. With all of these, you have the problem that they are ill-posed problems in the sense that you can take very different fitting parameters, right? So if you take this sort of nucleation, elongation, fragmentation, and look at these rate constants, each of these lines is picked from an ensemble of solutions where those rate parameters vary by 4 orders of magnitude. So you have very little insight into what's actually happening to the, say, the nucleation rate or the elongation rate or anything else like that. So this is work that was recently published. I'm not going to spend too much time on it, but by using this Bayesian computation technique, you can essentially generate an ensemble of solutions, and that ensemble of solutions reflects the original uncertainty in the experimental data and the structure of the model itself. So in the case of this model, you may not know exactly what the nucleation rate is by itself, but you can say with great precision how much it changes relative to its initial value as you're titrating heparin in. And so with heparin, what we see is that as you start off adding heparin, you see a slight shortening of the T50 and you see an increase in that plateau. Past some optimal concentration, you then see a slowing down of that aggregation. So you have a biphasic response, and we can interpret that quantitatively in terms of heparin strongly inhibits the dissociation of monomer from a growing fibril, and somewhat less strongly it promotes primary nucleation. It's not having much of an effect on secondary nucleation processes. And since I've got just about 30 seconds left, I'm going to skip ahead and say that we also have computational efforts in progress where we're basically trying to use computer simulations to model the ensemble of tau, identify within this ensemble locally structured states that are preferentially sampled that are potential drug targets, using these as drug targets, stepping through computational docking and machine learning driven screens, and ultimately ending up so far with, we've got 10 compounds that were generated by this computational pipeline, and in vitro have activity. Compound 10 appears to enhance the plateau of the aggregation, and compound 1 increases the T50 and decreases the plateau. So we're at a stage now where, given our work on polyanions and chaperones, we think that certainly the different effects of different modulators can be understood in terms of an understanding of the aggregation pathway and what states are being selectively interacted with. And then preliminarily, it does seem like we're able to use well-established computational methods to develop new ligands for disordered targets like tau. And so I know that I'm standing between you and lunch, so I'm going to stop right here. And I'll take any questions. I've got a poster number 72. If you need more details, if you're curious about anything, come talk to me.
Thank you very much for this very clear presentation. We have time for questions.
So Matt, you want to go ahead?
Right. Oh, yeah. So do you know how stable those oligomers that HSP70 puts tau into? And if you took away HSP70 or had a way to take it away, how long do they persist?
That's a great question. We haven't been able to figure out a way to take the HSP70 out. We also looked for, is there the ability to reverse fiber formation? That sort of disaggregation has been seen in other systems. We don't see it ourselves. It may be just a question of finding the right conditions for it. But, yeah.
So I have just a quick question. So have you studied a range of concentration of HSP to see whether at a lower concentration regime it actually promotes fibril formation by sort of cleaving the fibrils and making more ends because they're
Interesting.
and the higher concentration, because we have seen it for the yeast prion protein.
Sure, yeah.
That at a lower concentration, actually the chaperones promote fibril formation. And at a higher concentration, it inhibits, it dissolves the fibrils.
Right. No, that's a great suggestion. The lowest we've gone with HSC70 is 1 to 100. So
there are quite a number of papers by Susan Lindquist about 10 years ago to show that, there is a switch.
Absolutely, yeah. And I think it sort of depends on how predominant secondary nucleation is going to be for this system.
Hello. I was interested in the mechanism of action of HSP70 on the tau aggregation process.
Yes.
As far as I understood, it's trapping the oligomers, and I would expect they increase the toxicity in this case because the oligomers are the toxic species. Have you had a chance to measure the toxicity, the resulting toxicity?
That's a great suggestion. That's something that's definitely in the works. Yeah. And it's also going to be a question of what types of oligomers is it trapping them in? So yeah.
Yeah, he asked my question. But anyway, in addition to test the toxicity, have you tested if the small piece with the chaperone would see the aggregation?
A small piece of the chaperone would see.
Well, in the case that you have inhibition of the fibrils, if those material would see the aggregation of tau.
So you're saying for the HSPB1 fibers, for instance, where we have presumably some sort of, we haven't. That's an easy thing for us to do. Yeah, it's an interesting question.
Okay, the last question.
Thank you. Very interesting. If you look on the EM that you showed, which shows that really tiny sort of curvilinear protofibrillar structures, is HSP70 a part of those aggregates, or is it this transient interaction?
Yeah, so we've actually been doing immunogold labeling to try and answer exactly that. And so far with the antibodies that we have too much sort of a background situation to really answer that. But that would be great to know whether we, also in the case of the fibers, whether we have, we can see dots of gold at the end of each fiber. Yeah.
Okay, so thank you very much. I want to thank both speakers of the young researcher session and all speakers of this morning. And probably Samrat has some announcements.
So thanks, Thomas, and both the speakers. So just to remind you, tonight we have a conference banquet at a hotel in the city, which is about 15 kilometers and 10 miles from here. So the buses will start here at 6:30. So there will be quite a few buses because we are, so that's just to remind you. And I think people would probably prefer to walk to the lunch venue. That's what people did yesterday. So you are welcome to enjoy the weather. And the weather has really aligned with our wishes.